So by the 1960s, they'd only discovered 4 leptons, but there were hundreds of hadrons. In fact, this was how you got your PhD in physics, was you discovered another hadron. The leptons seemed elementary and small. They were very, very small. But the feeling, the thought was that not all hadrons, and these are mesons and baryons, right? Not all of those could be elementary. In fact, they're actually showing some sort of internal structure with the Stanford Linear Accelerator. So Murray Gell-Mann suggests that hadrons are actually made up of quarks, okay, which is a word that comes from a James Joyce book, Finnegan's Wake, which he named after a racist song that the British wrote about the Irish, and the Irish ended up embracing this song. Anyway, you'll have to look it up. The Clancy brothers do a rather rousing version of this. But anyway, basically there are 12 particles and antiparticles, right? So 6 quarks, and then there are antiquarks, right? The top quark, I don't believe, makes up hadrons. Okay, it's a heavy thing. It's like 173.1 giga electron volts. But all the other ones make up hadrons. Notice that they have fractional charge, right? And the antiparticles have the same charge, only it's negative, right? Remember, baryons are quark, 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 right? So up, down, charm could be a baryon, right? Remember that mesons are quark, anti-quark, right? Okay. Quarks inside baryons and mesons are held together by gluons, and as you separate them, the force doesn't get less with distance, it actually increases. We don't believe that we've ever observed free quarks. Let's just say they're always bound up in baryons and mesons, at least at this energy level. Okay. Here, and this is fun. You can make your own hadrons here, right? This is a proton. You need to memorize protons. So a proton is up, down, up, right? And the neutron is ud, up, down, down, right? And if you look at this, you can see that 2/3 of a charge plus 2/3 of a charge, take away a third, right? For the emperor, you end up with +1, right? A neutron, you have 2/3, but then you have 2 negative 1/3 charges, so this is 0 charge. A pi plus is 2/3 plus 1/3, right? Pi minus is minus 2/3, right? It's the same 2 quarks, only it's the anti, right? Okay. So anyway, yeah. So do memorize the makeup of a proton and a neutron. You should memorize this. That's IB says you should. I feel you should too. Okay. I'll always give you the mesons and also the other hadrons besides that. I think this is just a table. The best place to research particle physics, go on to Wikipedia, and it's at least as good as any particle physics textbook. And you can see here's the quark content here. You've got up, up, down, that's your proton, up, down, down is your neutron, right? And then there's all these other ones, right? Then you can just look these up. That gives them all of these different properties, right? We're going to look at strangeness, but not charmedness or charm, right? Anyway, so let's look at some of these guys. Let's figure out the properties of them. Okay, so let's look at the charge, right? So an up. If we look at up for charge, it's going to be, let's find up. Up is 2/3, right? And that's a regular up, so it's 2/3. And then there's another up, so it's 2/3. And then it's a down, and a down is, let's see, minus 1/3. So that's +1, right? So proton is +1 for charge. Let's look at the strangeness. Well, there is no strange quark. Strange quark has a strangeness number of -1, okay? And so there is no strangeness, it's 0. Let's look at the baryon number. All of these, by the way, have a baryon number of 1/3, so it's 1/3 plus 1/3 plus 1/3 is 1. So it is a baryon, it has a charge of +1, it's a proton, okay? And by the way, not all baryons are protons, but there it is. Let's look at the neutron then, just for fun. Let's look at the Jimmy Neutron. Okay, so strangeness, again, there's no strange quark. Charge is up is, let's see, up is 2/3. And then 2 downs is -1/3, -1/3. So the charge is 0, and then the baryon number is 1/3 plus 1/3, plus 1/3. So that's 1. So it's a baryon. It has no charge. All right. Let's see. Let's look at a lambda. Let's look at lambda naught, up-down strange, shall we? Okay, so this guy, let's see, 2/3. That's 2/3. The charge is 2/3. Let's see, down is minus 1/3. Strange quark is also minus 1/3. So it has no charge. That's, by the way, why it's a lambda naught. Okay, no charge there. Let's look at the baryon number. That's 1/3 plus 1/3 plus 1/3. There's 1. Okay, let's look at the strange. Well, all quarks have a strangeness number of 0, except the strange quark has a strangeness number of minus 1. So this guy's minus 1. Okay, how strange. Okay, let's look at charm, the charmed lambda. Okay, its charge is up. Up is 2/3. Oops, charge 2/3. Right. Okay, let's see. Down is minus 1/3. And then charmed quark is positive 2/3. So this adds up to 1. Charge is plus 1. That's why it's got a plus on it, right? By the way, nobody puts a plus on a proton, but that's okay. I guess to distinguish it from its antiparticle, maybe you could. I don't know. Okay, so let's see. Is there any strangeness to this guy? No. No strange quark. And then it's going to have a baryon number of 1 because it's 3 quarks, 3 1/3. All right, final one. Let's look at the bottom lambda. Let's see, up is 2/3. Oops, charge 2/3. Down is minus 1/3. And then the bottom quark is minus 1/3. Then that's 0, right? That's why it's got a little 0 on it like that. It is a baryon, so it's got 1. It's 1/3, 1/3, 1/3. It has 0 strangeness. All right. Anyway, this is the hard-hitting science that we're going to do with this. Okay. Now this is kind of fun. These are some mesons, right? And notice the pion. Why it's the regular pion is up, anti-down, right? The pi minus. This is our pi plus, right? That's the matter particle. The antimatter particle is pi minus is anti-up. Down, right? Okay. So that's kind of fun. So all of these guys are quark anti-quark pairs, right? But check this one out. It's like, what's going on there? Okay. This is, what is this called? Superposition or something like that. This is an indeterminate one. So the pi naught. Okay. If you observe it, it's either going to be up anti-up or down anti-down. Okay. Which one? Well, when you observe it, I'll tell you. Okay. It's going to be one or the other, but not both, right? The reason that there's a square root of 2 on the bottom is that that's a normalization coefficient. You square these equations to get the probability, and basically we're saying half of this and half of that. Okay, it's half the time going to be this, half the time this. Okay, that's fun. So these are indeterminate mesons, right? So there's more to this than we're learning in IB. Okay, so let's look at these guys here. Let's look at the numbers of this. Okay, so let's draw some lines here. You got to draw a line. Okay, the baryon number, well, let me just say these guys are going to have baryon numbers of 0, right? So this is a 1/3 baryon number plus a minus 1/3, right? Because the anti-quarks have a minus 1/3, so this guy's 0. There's no strange quarks, right? So this is 0. Let's look at the charge of this guy. Up, anti-down. So up is 2/3. Down will be minus 1/3, but an anti-down is plus 1/3. So that's plus 1, right? Okay, let's imagine that we observe the pi naught and it's in the up, anti-up state. Again, the baryon number is going to be 0. You're going to have a positive 1/3 and a negative 1/3 for that. So that goes away. There's no strange quarks there at up, anti-up. And then let's look at the charge. Up is 2/3. And anti-up would be minus 2/3, right? Right? And down, anti-down would also have 0 charge, right? Which is why it's a pi naught, right? Let's look at the eta. Eta, the charmed eta. It's a charming eta. All right, so this is baryon number, strangeness, charge. Let's see, the baryon number is, of course, going to be 0, right, because it's charm, anti-charm. So charm is 1/3, anti-charm is -1/3. There's no strange quark here, right? Let's look at the charge. Well, of course, the charge got to be 0. So whatever it is, the other one's going to be opposite that. So 2/3 minus 2/3 is 0. So the eta, the charmed eta, has no charge. All right. One of the cool things about quarks is that they form these octets. And this is a bit like the periodic table. You can have axes like strangeness numbers like this. You can have charge numbers. And if you line them up like this and you draw lines through them, you can predict the existence of hadrons or mesons in this case, right? You can predict their existence. And so, for example, you can discover all of these guys, and then it's like, but we haven't discovered that one yet. Well, we're going to, okay? It's a bit like the periodic table. Is it Mendeleev? You know, it's like there's a blank spot on the periodic table. I'll bet we'll find that element, okay? Anyway, obviously you can just get lost in this thing. These are the truly fundamental particles, okay? So the quarks, and they're in generations. This is lighter, and they go to heavier, right? Top quark is a chunker, right? Okay. And so we've got up and down, electron, neutrino. That's our first generation, right? And the first generation gauge boson is our photon, right? Our second, these are a bit more hefty, right? Is our strange and charmed quark, and then the muon and the mu neutrino. Did I say electron neutrino? Hopefully I did. All right, and then over here, these are heavier, right? So gluons, these things mediate the strong nuclear force. These are the weak. These together, by the way, are the electroweak force. But anyway, this is one way to organize them like that. 3 generations. The top quark is a chunker. I don't believe the top quark makes hadrons. And then, of course, there's the Higgs boson, right? So we need to add to the scalar bosons. Read about the Higgs boson, right? What's the symbol for it? Is it an H? I don't even know. I don't know. Okay, the Higgs. I'm just going to write Higgs. Okay. So all of these guys are spin 1, right? This is spin 0. And then these guys are fractional spin. Okay, so these are your bosons. These guys are fermions. Here you can see it here, right? So all of these spin 1/2 things are fermions. These obey the physics of Fermi and Dirac. Bosons obey a different set of laws. Remember, fermions can't be in the same quantum state, but these guys congregate there when they get cold, like in superconductors and such. So here's our scalar boson, right? Here are our gauge bosons. These guys mediate forces. This guy gives mass to the particles. Mediate forces, right? The photon, the electromagnetic force, the gluon, the strong nuclear, and this is the weak nuclear force, right? And then these are our leptons, these are our quarks, okay? Yeah, it's a model.